Now we turn to the very last part of the course on power series and its applications. Now recall that we have seen that the series from 1 to infinity of x to the n over n factorial is absolutely convergent for all x. And the way we have seen that, we've seen that along the way to prove that the limit of the sequence of general term is 0 for every x. And that was because the series was convergent for every x. So to show that, we used the ratio test, and when you take the ratio of two consecutive terms in absolute value, taking into account the cancellation from n factorial divided by n plus 1 factorial gives us just n plus 1 at the bottom. Absolute value of x to the n plus 1 divided by absolute value of x to the n just gives us absolute value of x at the top. And when n goes to infinity, this quantity goes to 0, which is less than 1. So that means that regardless of what x is, the series is absolutely convergent by the ratio test. And what that means is that for each x, we can associate the sum of the corresponding series. And it's a well-defined number, and therefore we have a well-defined function on the real line. Now this series that depends on x, right, the sum is over the index n, but inside we have a variable x that can take real values. This is what we will call a power series. This is an example of a power series. And a power series, in the case centered at 0, we'll see a more general presentation of them later on, is a series that takes a form of essentially a polynomial of infinite degree. So it's a sum from 0 to infinity of a coefficient that depends on n, right? It varies with n, multiplied by x to the n. So that means it starts with a constant c0, and then a constant c1 times x, and then a constant c2 times x squared, and so on. So it's like a, as I said, like a polynomial, but of infinite degree. X is a variable, each one of the Cn is a constant, which of course depends on n. These constants are called the coefficients of the power series. So now, you see that if you want to think of the sum of a power series as a function of x, it really is a well-defined function only for values of x that makes the series convergent. And so we can ask, okay, what values of x makes a series convergent? So let's look at some example, starting with a case where we take all the coefficients equal to 1. Then for each x that is fixed, we have a series, say from 0 to infinity, of x to the n, and that's really just the sum of the powers of x, and therefore it is a geometric series of common ratio x, and we know when that is convergent. It is convergent exactly when the common ratio in absolute value is less than 1, which means in our case if x is strictly between -1 and 1. And additionally, in that case, we know what is the sum of the geometric series. It is the first term, which in this case is x to the 0, which is 1, divided by 1 minus the common ratio, which is x. So we get that for x between -1 and 1, the sum of the series is 1 over 1 minus x. And that's a function with domain -1, 1. So here we have a power series that we can think of as a function of x, at least for x strictly between -1 and 1. We can also turn that around in some way and think of it as we know the function 1 over 1 minus x, and we want to represent it as a series, a sum of a series, and what we have here is that the function 1 over 1 minus x can be represented as a power series on this interval between -1 and 1. We'll talk more about how to represent various kinds of functions as power series later on in this module. Now you might ask, why do we want to do that? Well, the fact that these power series are generalized polynomials means that they share some practical aspects of polynomial, and we will see that it's very convenient to have a function written as the sum of a power series. Another observation is that there's always at least one point where the series is convergent. When x is 0, if you plug x equals 0 in your series, then all the terms in the series are 0 except the first one, which is c0. So then you get just the first term C0 of the series as the sum of the series. So you have always at least x equals 0 where the series is convergent. On the other end, we've seen that we've seen an example of a power series converging between -1 and 1, and another example converging everywhere. So legitimate general question is for what values of x is a given power series convergent. So we've seen an example where it's convergent on an open interval, an example where it's convergent everywhere. And let's look at this other example where the coefficient Cn is just n factorial. We're going to look at convergence in terms of the ratio test, and therefore calling an the general term n factorial x to the n, we look at the absolute value of the ratio of two consecutive terms. So we get n plus 1 factorial absolute value of x to the n plus 1 divided by n factorial absolute value of x to the n. Absolute value of x to the n plus 1 divided by absolute value of x to the n is just absolute value of x, and n plus 1 factorial over n factorial just n plus 1, so we get n plus 1 multiplied by x. If x is 0, we get 0 and the series is convergent, and if x is not 0, this goes to infinity when n goes to infinity. And therefore, if the limit of this ratio is infinity, then by the ratio test we can conclude that the series is divergent. In other words, this series converges exactly if x equals 0, so only at one point. Let's look at one more example. The series from 1 to infinity, I'm going to start at 1 and not at 0. In other words, I'm taking C0 equals 0. A series of x to the n over n. Again, we're going to look at convergence in terms of the ratio test. So we call an the general term, x to the n over n, and look at the absolute value of the ratio of two consecutive terms. As usual, the absolute value of x to the power n plus 1 divided by absolute value of x to the power n simplifies as simply absolute value of x. And what remains is n over n plus 1, which goes to 1 as n goes to infinity, which means that the limit of this absolute value of the ratio of two consecutive terms is absolute value of x. The conclusion from the ratio test is that if this absolute value of x is strictly less than 1, then our series is absolutely convergent. If it is strictly greater than 1, then it is divergent. So what if it is exactly 1? Well, there's 2 points where the absolute value of x is 1, x equal 1 and x equal -1. And we can look at what happens at these points. When x is 1, if I plug x equal 1 in my series, 1 to the n is always 1, so I get the series from 1 to infinity of 1 over n, which is a divergent p-series because it's for p equal 1, which is less than or equal to 1. So it's divergent for x equal 1. On the other end, for x equal -1, if I plug that value of x inside my series, I get the series of -1 to the n over n, and that's an alternating series, where the sequence of absolute value of the general term is 1 over n, which is a decreasing sequence with limit 0, and therefore by the alternating series test, it is a convergent series. So we have absolute convergence strictly between -1 and 1, divergence if x is strictly less than -1 or greater than 1. For x equal 1, it is divergent. For x equal -1, it is convergent. In other words, the series converges for x in the interval -1, 1, where we include -1 but exclude 1. So you see that we can have, for these examples at least, an open interval centered at the origin. All x, which we can think as an open interval centered at the origin, but which extends as far as we want on both sides. Something that we can think of as an interval centered at the origin, but reduced to simply the origin. Or an interval centered at the origin, where we may or may not include the endpoints. So it looks like maybe such power series converge on an interval centered at the origin. And indeed this is the case, but we're going to look at that in a more general context, where we're looking at power series centered at some value a, and that's a series of the form sum from 0 to infinity of a coefficient Cn, which is a constant that depends on n, multiplied by the nth power of x minus a. So that's a constant C0 plus a constant C1 times x minus a, constant C2 times x minus a squared, and so on. And our general result is that for such a power series, and of course the case we discussed before is a case where a is 0, centered at 0, then we have only three cases. Either the series converges only for x equal a. We've seen a case like that when we were looking at examples centered at 0. Or the series converges for all x. We've seen a case like that as well. Or there is a finite number r that is not 0, such that the series converges whenever the distance between x and a is less than r, and diverges whenever the distance is greater than r. So let's look at what that means, starting with the third case. Here is the real line, and let's pick our number a. And we are looking at this condition that the distance between x and a is less than r. In other words, x is between a minus r and a plus r. It's in the open interval with endpoints a minus r, a plus r. This is the red open interval that we have here. It's an interval centered at a. Now, the condition inside this dotted rectangle does not include the endpoint. We have the open interval. The question of convergence at the endpoint is not determined in this theorem. We don't know if a minus r or a plus r are values of x that make the series convergent in that case, and we'll see that in general, if we want to find all the points of x where the series is convergent, we have to test these endpoints individually. R will be called the radius of convergence of the power series. In this case 2, where it's converging for all x, we can think of it as a particular case of case 3, where R is infinite, and therefore our interval centered at a extends all the way across the real line. Similarly, the first case, where the series is converging only at x equal a, can be thought of as the case where r is 0 and the entire interval centered at a collapses on the singleton a. So that will be the case where r is equal to 0. In other words, we include 1 and 2 in some sense in case 3 by allowing r to take the value 0 or infinity. The interval of convergence of the power series is the set of values of x for which the series converges. So that's going to be an interval centered at a, so something that extends from a minus r to a plus r, assuming for instance that we're in case 3 where r is a non-zero positive number. And the endpoint may or may not be included in the interval. So we have this interval and possibly one or both of the endpoints, or not. So I'm not going to give a formal proof of this theorem, but indicate where it comes from. And it is easy to believe this theorem if you believe that we have this situation, that if a power series like that converges for a certain value of x, let's say x equal b, then it also converges absolutely for all x that are closer to a than b. Right? So the distance from x to a is less than the distance from b to a. And to see that, you have to realize that if the series converges for x equal b, then because of the nth term test, we know that the sequence of general term, so the sequence Cn multiplied by b minus a to the n has to converge to 0, and therefore the sequence of absolute value of these things also goes to 0. So for n large enough, we can make this expression absolute value of Cn b minus a to the n less than 1. Or in other words, we can make the coefficient Cn in absolute value less than 1 over the absolute value of b minus a to the n. Of course, here we are assuming that b is not a, because that wouldn't tell us anything if b is equal to a. But if this is the case, then multiplying both sides by absolute value of x minus a to the n, this is what we obtain. And on the right hand side, you have this x minus a divided by b minus a. And we're in the case where we assume that x is closer to a than b, and therefore what is under the parenthesis, absolute value of x minus a divided by absolute value of b minus a, is something less than 1. So on the right hand side we have the general term of a geometric sequence of common ratio less than 1. And therefore the corresponding series is a convergent geometric series, and by comparison the series with a smaller general term is also convergent, which gives us absolute convergence of the power series for an x that is closer to a than b. In particular, you should see that in the theorem for 2 and 3, when we have convergence, we have actually absolute convergence in this statement. Now in 3 you also have a part about the fact that the power series diverges if the distance from x to a is larger than r, and you can easily imagine that we can use the same type of argument that we have used to prove that if the power series converges for x equal b, then it converges for every x that is closer to a than b. Then you can apply the same type of reasoning to show that if it's divergent for x equal b, then it's also going to be divergent for an x that is further away from a than b, just by using the same argument and comparing the series with a geometric series that this time would have a common ratio greater than 1 and would be divergent. Now here we just looked at the general situation and didn't really calculate this interval of convergence for many series. That's what we will do in the next video.